Everybody. So I'm going to try to make this as fast as I can, but still, explain things well. So you were supposed to have for today finished pages 2 and 3. And so this is page 2. Now remember, I erased it. Oh, no. So this is what we had last time for number 7. So number 7, we found out that the rise was positive 4 meters, the run was 4 seconds. We did positive 4 meters over a 4-second time interval, which again is the delta x over the delta t. The change in position was 4 meters. The change in time was 4 seconds. So a 4 to 4 or a 1 to 1 now, a positive 1 meter per second velocity. And that happened for 4 seconds total, which is why our VT graph has the line at positive 1 meter per second for 4 seconds. Okay. And then you were supposed to take a look at these and do the same thing. Now remember, when we're dealing with, especially with motion maps, there are the 3 things we were talking about before. Where did it start? What direction is it going? And what can you tell me about the velocity? Those are the 3 things we need to keep in mind. So for the first one here, we are dealing with a rise and a run. We're dealing with velocity being a change in position over a change in time. We have to know both of those. And again, these 2 graphs, unlike what we've been looking at, they have 2 different steepnesses going on. All right, 2 different steepnesses. We got to figure out the first one, deal with it, and then the second one, and deal with it. So I'm going to kind of go fast through here, and I hope you're able to see what I'm talking about. Oh, dang it, I need to, let's see. Let's do that. And, oh no, I need the skinny line. I'm in the way. Skinny line, there we go. Okay, so we have this first part here, the first section. We have a rise of positive 2 meters. We have a run of 1 second. So our delta x over our delta t, or again, our velocity, that's what that is positive 2 meters over 1 second. That is obviously positive 2 meters per second. So I hope you see that that's what's going on here. We have the first part here that is a 2 to 1. It's a 2 meters for every second velocity. Now, what do you do with that here? Where is positive 2 meters per second? Right there. How long did this happen? For how long, time-wise, did this happen? 1 second. This was only happening for 1 second. So you go to the VT graph, and at positive 2 meters per second, you draw a line that only goes over to the 1 second mark because it was only happening for 1 second. Now we have the second part, which is another rise section, which is positive 2 meters, like the last one, only this time that's happening over a 4-second time interval. So now we have, again, change in position of positive 2 meters, that's your delta x, over the time interval of 4 seconds, which gives us 0.5, positive 0.5 meters for every second. I hope you see that that's how that worked. Again, we're just looking at another rise over run. Remember, the rise over the run, or the slope of this position time graph, all position time graphs, that is velocity, which we need the number to be able to know where to put our line here. It's positive because it's a positive slope. It's a positive change in position. Only 0.5 now meters per second. Where's 0.5? Well, it's halfway between 0 and 1, right? So do we start the line here? I'd say no, because that started happening when? Time 1 second. Time 1 second is when the slope value changed. It is no longer 2 meters per second, it's now only a half a meter per second in the positive. That's down here. So, what the heck is that little thing doing out there? I don't know. So it's half a meter per second, and it did that for the remaining time. Oh, I don't like the double. I don't like the double line. Half meter per second for there. I'll just leave that. Whoa, what the heck happened there? Oh my gosh, the back is a. Oh, I need the eraser. Now we still need to do the motion map. So, motion map. Well, where did the object start in this little graph here? Where did it start? At the 0 position. So I draw my first dot on the 0 position. 0 position. What direction is it traveling? Positive. How fast? At 2 meters per second. That's faster at the beginning than it was later. So my first arrow is probably going to be pretty long. And that happened for 1 second. Then what happened? It was slower for 4 seconds. So I would draw 4 more arrows that are short. Why short? Because it's only a half a meter per second. This was 2 meters per second. This was only a half a meter per second. So I would say that 1, 2, 3, 4, 5 seconds, this was happening for 5 seconds total. 1 second was fast, 4 seconds were slow. There you go. Got that? I hope. Now, second graph. We have this section. Starts at 2 meters, ends at 4 meters. That's how much rise. How much change in position do we have here? That's a positive 2 meter change in position. How long did that take? That took 2 seconds. What is positive 2 meters over 2 seconds in time? Well, that's positive 1 meter per second. How long was that happening? 2 seconds. Positive 1 meter per second for 2 seconds. You see what I'm doing there? I find the slope. I translate that into the VT graph. Positive 1 slope for 2 seconds. The next section. Now, instead of going up, my slope is actually going down. So now I have not a rise, I have a fall. I have negative 4 meters. It went down from 4 to 0. That is a 4 meter drop, okay? 4 meter drop. That's a negative 4 meter change. And how long did that take? Well, that took 2 seconds, which means my change in position, my delta x, is negative 4 meters over a time interval of 2 seconds. That's a total of what? That's negative 2 meters per second. And that's my velocity. Negative 2 meters per second. Where's that? That's down here. But when did it start? It started doing that at time 2 seconds to 4. From 2 to 4 seconds, it was at negative 2 meters per second. Hopefully you see that that's how that should look. Now, how about the motion map? Well, again, what are our 3 questions we have to answer? Where did you start? What direction did you go? And how fast was it? Well, where did this object start? Not at the 0, right? That'd be here. It's a positive 2 meter position, started. So I'm going to put my first dot out here somewhere away from the 0 and the positive. What direction is it going? Well, positive slope. That's positive direction. How long? For 2 seconds. So I need 2 dots and arrows in the positive direction at positive 1 meter per second. Something like that. Then what happens? Object turns around. Now there's a negative slope, and the negative slope means negative velocity. Negative velocity means the other way now. Going back toward the what? Where does this object get to at the end? At the end of the 4th second, the object is at the 0 position. Goes past the starting point of 2 meters and gets all the way to the 0 position. How long did that take? 1, 2 seconds. So you're telling me I've got to get from here all the way back to the 0 position. I shouldn't say back to the 0 because it never was at the 0. I got to get all the way to the 0 position and only take 2 seconds to do it. So how many arrows am I allowed to use? 2, because that's 1 arrow for each dot, and that's 1 dot for each second, and there's only 2 seconds. So what does that tell you about my arrows on the return? I guess on the return. No, on the return. I can't get the mirror thing going on. So I have to draw these arrows bigger. Why? Because it's twice as fast. Look, 2 is twice as fast as 1. Remember, the negative doesn't mean it's small. It means it's in the negative direction. I'm pointing the wrong way. In the negative direction is what the negative means. So I hope, or no, oh my gosh, that is negative. Oh my gosh. See, I don't know how you're seeing me, seeing it, if it's a reflection or if it flips it back around. Oh gosh, I apologize. Negative direction. All I know is it's a negative direction. So I put my dot down here because that's this wherever the last arrow ended, that's where I'm putting my new dot. Because now it's got to go back the other way. And the arrows have to be twice as long as what they just were. I hope that makes sense. This should be what your motion map looks like. It went in the positive direction, starting from a positive position for 2 seconds. Then it turned around and went all the way past where it started into the 0 position, and it only took 2 seconds. And so it did that way faster, so way longer arrows. I hope that makes sense. So that's page 2. Page 3. Now, some of this I already have done. And I'm just going to walk you through like what I did here. It was what we were just doing. Well, first of all, hopefully you plotted the XT graph and it looks something like this. If it didn't, then we may have a problem there. Now, how on earth did all these lines get put where they got put? Well, let's take a look. The first section, what's the steepness of that first section? The steepness of the first section is, now I realize my graphs probably don't look like yours. You probably went by 1s. You probably went on your grid by 1s for your interval. I'm by 2s here because my grid wasn't big enough. My boxes are too big. So if you may be looking at yours thinking, oh, mine's not right. None of this looks right. This doesn't look the same as mine. Remember, these are by 2s. You probably went by 1s. So don't think you're not right just because it doesn't look exactly like mine does. So that's a rise of 4 meters, a run of 2 seconds. A 4 meter over 2 second run. What is that? Well, that's, again, positive 4 meters, 2 seconds. Positive 4 meters over 2 seconds. That's a velocity of what? Positive 2 meters per second. That's your velocity. Notice what I did on the VT graph. On the VT graph, what did I do? I drew a line at positive 2 meters per second, and that lasted for 2 seconds. So again, I found the slope. I drew my line on the VT graph at the place where the slope told me to draw it, and for how long of time the graph told me to draw it, for 2 seconds. Second section here, it's horizontal, which means there's how much slope? None. No slope means no velocity. How long did this happen? 1 second. So I drew a horizontal line on the 0 velocity for the 3rd second, which is when this happened, during second 3, 3rd second. Then I went to the next section. Notice it's 6 meters tall. This section here, I should change to another color. Oh, I can't because I just blocked my pen. I don't care. So this is positive. Oh my gosh, it's going nuts. Oh, no. Oh no, what just happened? Undo. I don't know what. That is positive 6 meters, and that's 2 seconds. So what's positive 6 meters over 2 seconds? Well, I hope you can clearly see that that would be 3, right? Positive 3 meters per second, which is where I put the line here at positive 3 meters per second for 2 seconds again. Then we have another section that's horizontal, no slope, zero velocity, and that line went down here on, again, the zero velocity axis, on the t-axis at zero velocity between seconds 5 and 7, which is when that happened. And then finally, we have the last section, which is not a rise, but rather a fall. It's a, I should have left that on there. That was positive 6 meters, we said. And that was positive 4 meters. And now we have this. That's 10. It starts at 10 meters, goes to 0. That's a change of negative 10 meters. Do you see that's a negative 10 meter change? Because when you go from 10 to 0, you're going down in the negative direction. And that took 2 seconds. So what's that? That's negative 10 meters over a 2-second time interval. Again, that's your velocity, your delta x over your delta t, and that is negative 5 meters per second. Well, what do we see here? Oh, look at that. I drew a line there at the negative 5. And when did I draw the line? From 7 to 9 seconds. Do you see that? I hope you see that. So each of these 5 lines here on my VT graph represent each of the 5 sections. That's section 1, where I was positive 2 meters per second. Here's section 2, where I wasn't moving at all. Here's section 3, where I was positive 3 meters per second. Here's section 4, where I wasn't moving at all. And here's section 5, where we were moving at negative 5 meters per second. And we see that on the graph here. Okay? Hopefully that makes sense when you transfer position time stuff to velocity time stuff. Now, you're supposed to make a motion map. And I already have it drawn here. So that is what your motion map, I think, should look like. Now, why should it look like that? Well, where did we start? 0 position. Traveling in the what direction? Positive. For how long? 1, 2 seconds. That's what this is right here. This little section, that's the first section. Then what about this 1 second? 1 second not moving. That's a dot, no arrow. Dot with no arrow means not moving. Then what? Then we pick up and start moving again, faster than before. Faster than the 2 meters per second. Now we're at 3 meters per second, and that happens for 2 seconds as well. So how many arrows did I put? 1, 2. Then what does the object do? At the end of that period of time, we again have a flat spot up here that I'm in the way for. We have a flat spot up here. And that's 1 dot, 2 dots, no arrows. At rest, not moving, no arrows. Then what do we do for the last part? Well, let's think about this. How long do we have left? 2 seconds. Where does this object have to get at the end of the 2 seconds? All the way back to the what? To the 0 position. All the way back to the 0 position. That means my 2 arrows have to be long. 1 arrow, 2 arrows getting back to the 0 position. How fast was the object then? 5 meters per second. But again, in the negative direction. Okay? Negative direction at 5 meters per second. Longest arrows. I hope that makes sense. So we have all 5 sections represented. There's section 1, section 2, section 3, section 4, and lastly, section 5. Those are the 5 sections. Now, the next two questions, it said determine the displacement from 3 to 5 seconds using graph B. Well, technically, they want you to use this. This is what they're calling graph B, the VT graph. But I want to look back over here. How do you know what the displacement is from 3 to 5 seconds? Well, how much did your position change from 3 to 5 seconds? We have it written down right here. That's how we found the slope. Yeah, that's how we said the displacement or the change in position was from 4 to 10. That's how much. That's positive 6 meters of change in position, right? Now, we said last week, which maybe you've already forgotten, I don't know, that displacement is change in position. That's what displacement is. It is change in position. By definition, that's what we call it, which is the final minus the initial. What's the final? From 3 to 5 seconds, what's the final? In other words, where is the object at 5 seconds? 10 meters. Object is at 10 meters. That's the final position. Final position is 10 meters. Oh, dang. Final position is 10 seconds. 10 meters. 10 meters final position. Minus, where was it at the beginning? 4 meters. It was at 10 at the end, minus where it started of 4 meters. That's a change in position of positive 6 meters, 6 meters in the positive direction. That's where it comes from. Final minus initial. It always works. Then they ask, how about from 7 to 9 seconds? 7 to 9 seconds. And look, the answer is negative 10, yes. And how do we know that? Because it started at 10 and went to 0. Started at 10, went to 0. That is a negative 10 meter change. Well, how does it work with this? Well, let's think about it. Where was the object at the start? Or excuse me, at the end. At the end, where was the object? It got back to the 0. It was at 0 meters at the end. Final position. It was 0 meters at the end. Minus, where did it start? Where was the initial position? Well, it started at 7 seconds. It was at 10 meters. It was at 10 meter position at the beginning of this time interval. So what's 0 meters minus 10 meters? Negative 10 meters of change. Negative 10 meters of change. Okay? I hope you're seeing this right here, the final minus the initial, it's always going to work. But I hope you see that when you look at the position time graph, when you look at how much the position changes or goes up and down during a segment of time, you can see it right on the graph. I mean, we already figured those out. During the first part, how much position change was there? Positive 4. During the third part, how much position change was there? Positive 6. During the last part, the fifth part, how much position change was there? Negative 10 meters. We found each of those delta x's, the delta x, we found it to find our velocity, our delta x over delta t. So all that's being asked for is, what is your delta x? What is your change in position, or your displacement, we call it. Now, I'm going to tell you this right here. You better write that down in your comp books. Area under the curve of a VT graph is delta x, or displacement. This is big. This is big right here. And I'm going to show you, I'm going to do some work on the graph and show you. I hope you follow along. This is big. Area under the curve. What I mean by that is this. Oh, I want a different color. Area under the curve. That little rectangle. By area, well, I realize that these aren't curved lines, but mathematically, we always say that the area, or that any line on a graph is called a curve, whether it's straight or curved. Don't ask, it just is. So the area between the line on the graph and the zero, or the t-axis. That's what we're looking for. The area between the line on the graph, and the t-axis. That is the area we're looking at. Now, does that box have dimensions? Like, does it have a height and width? Yeah. Well, what are they? Well, look at it. We have positive 2 meters per second rise, or I should say the top, or the height, sheesh, easy for you to say, times, what's the base? Well, it's 2 seconds. What do you get when you seconds cancel seconds there? And positive 2 meters times 2 is actually positive 4 meters. What did we say the displacement was during the first 2 seconds? Oh, look at that. It's positive 4 meters. That's the area of that box. Coincidence? I think not. How about the next section? There's a rectangle now. How tall is that? Well, it's positive 3 meters per second tall, and it's 2 seconds wide. Seconds cancel seconds, and what do you get when you take positive 3 meters times 2? Oh, you get positive 6 meters. Now, wait a minute. What did we say during that section the displacement was? The change in position was what? Positive 6 meters. Well, that's what this says. That's not a coincidence. It's the same thing. The area of that rectangle is the delta x, or change in position. What? How about the last segment? How about this section? Oh boy, I gotta draw a little line down there, draw a little line down here, and shade it in. How tall? How tall is that? Well, what does it say over here? That is what? Negative 5 meters per second tall. Times what? How wide is it? 2 seconds. Seconds cancel seconds. What's negative 5 meters times 2? Negative 10 meters. Is that not what we just said the displacement was, or change in position was, for the third segment here? I mean, the fifth segment. Negative 10 meters of displacement. So this right here, this area under the curve thing, that's a really important part of this unit. We have now found that if you just look at how much space there is, the area that's under now, again, you might be looking at this one saying, well, isn't that area above the curve? Well, we call it under. If it's between the line on the graph and the t-axis, then we call it under the curve. It's always, the box always has to be between the line on the graph and the t-axis, always. Now, hey, how's come there's no boxes here? In this section, there's no boxes. Because there's no height. There's no height. There's a width, there's no height. Well, how much area, if you don't have a height of a box, then you just have a line. How much area is that? None, because what didn't this thing do? It didn't change position for a second. And then it didn't change positions for 2 seconds. So there is no change in position. There's no delta x. There's no area to be found. Now, I asked 2 more questions in class. I said, what is the total displacement for the whole 9 seconds, the whole shooting match? How much displacement is there? Well, that's like asking, hey, what was your initial and your final position? Where did the object start? Position 0. Where did the object end? Position 0. How much displacement was there from beginning to end? 0 displacement. Well, yeah, but it went somewhere. Yeah, and it came back to where? Where it started. It came back to where it started. That means it is not displaced. At 9 seconds, at time 9 seconds on the clock, is it displaced from where it started? The answer is no. It is in the same place. as when it started. Therefore, it is not displaced. Now, think about this. What if you add positive 4 meters plus positive 6 meters plus negative 10 meters? What do you get? Positive 4 meters plus positive 6 meters plus negative 10 meters, you get what? 0 meters. If you add up all of your displacements, what do you get? Nothing, because you're not displaced. Now, were you displaced at time 2 seconds? Yeah, you were displaced by positive 4 meters. Were you displaced at time 5 seconds? Yeah, you were displaced by a total of positive 10 meters. So you were displaced at certain moments, but from beginning to end, you weren't displaced because you went back to where you started. Now, the second question is, how much distance was traveled? How much distance was traveled? Remember, distance is the length of the path that you traveled. So how much distance was traveled? Well, you went 4 and another 6 and then 10 back to 0. That's a total of what? That's 20 meters of distance. You traveled 20 meters total, but where did it get you? Well, as the motion map shows, back to where you started. You went 10 out and 10 back, but it got you right back to where you started. So you were not displaced, but you did travel 20 meters. I hope that makes sense. Okay, so next is you're going to do the final page, page 4. So you'll do page 4. That will be for the next time. And then, let's see, then hopefully we'll be able to finish that, do some review things that hopefully the next class after that is when we will take a test on this whole unit. So, page 4 for next time. I think that's it. I'm sorry this turned out to be so long. I tried to make it as fast as I could. Have a great day.